Alright, we're the BME 458 music makers. The objective of our project is to understand the waveforms generated by various sensors, detect changes in these waveforms based on the sensor stimulation that we input through various means, and correlate these changes in waves to a musical output. To do this, we must be able to control the music being played via sensor stimulation. So ultimately, our goal is to play Mary Had a Little Lamb. Our approach to this is using three different sensors: a pressure sensor, a potentiometer, and strain gauges, and putting these into different circuits, which then input into the data acquisition board, which sends the signal into LabVIEW for further manipulation. The pressure sensor is our drum, the potentiometer turns out to be a trombone, and the strain gauges act as our piano. So as you can see here, there's three different pictures. This is of our bass drum. If you squeeze this, it inputs airflow into our pressure sensor. It's a fluid pressure sensor. And then it outputs a bass drum sound from LabVIEW. With the trombone, we use this potentiometer to produce three different notes depending on where the slider is in the sliding mechanism. And for the piano, there are 4 different strain gauges. Only 3 of them were used for our project. And they output different notes to LabVIEW, which outputs different notes through the speakers. So here is our front panel and block diagram in LabVIEW. As you can see, it's DC output through all the sensors. Our primary results using the bass drum is the pressure sensor shows an increase in voltage when pressure is applied. We set a specific voltage threshold, and when that was reached, the drum beat sounded through LabVIEW, and that voltage threshold in our case was 200 millivolts. So when we pushed that little ball, it caused a voltage spike above 200 millivolts. For the trombone, the potentiometer voltage increases on an exponential scale. So different linear displacements cause different output voltages, as I was explaining before in that picture. When you set a voltage threshold for different displacements, when they're reached, trombone notes will sound in LabVIEW. And there's these 3 ranges that correspond to the different notes, A, B, and G. And the amplitude response of the human ear is logarithmic, which is a fun fact. For the piano, the strain gauge resistance changes with deformation. So as you push down on the metal key, the resistance changes in the strain gauge, which causes an output to the circuit in the Wheatstone bridge. So the voltage output changes linearly for small changes in strain gauge resistance, and this Wheatstone bridge determines the unknown and varying resistance of these strain gauges through these 3 sets of resistors. And the 4 strain gauges, well, technically 3, correspond to these 3 different notes, A, B, and G. It's also important to note through this Wheatstone bridge that small changes in resistance correspond to large changes in voltage. So here's the demonstration of our trombone. Alright, so that was the demonstration of the trombone. So here we have the demonstration of the piano/drum. And now here's the demonstration of the full band together.
Great. Mary had a little lamb, little lamb, little lamb. Mary had a little lamb whose fleece was white as snow.
Alright, well that was our full band. So essentially at the end of this, our conclusions and recommendations, we've determined that each type of sensor has a unique waveform, and that LabVIEW can accurately combine the signals and then separate and manipulate them. And the signals all occur at the same sampling rate because we only have one data acquisition board, so future work could be done using multiple DAQs to play instruments at different rates.
Thank you.
Thank you.